Assalamu alaikum student. Welcome to the 11th lecture of the course Experimental Nuclear Physics. In the last lecture, we were studying the energy gain of the linear accelerator and energy gain of the cyclotron, and we also studied some modification of the cyclotron, synchrocyclotron and asynchronous cyclotron. This lecture is the continuation of our previous lecture, and in this lecture we shall mainly focus on the synchrotron. So synchrotron are the most complex and expensive tools ever built. In general, like that of the other accelerator, their purpose is to accelerate the charged particles. Usually, accelerator accelerate the charged particles, usually electrons, protons, and also isotopes, as well as subatomic particles, to incredibly high speed. The particles are used to treat the tumors or cancers inside the patients. These particles slams into the materials to study the mapping of the material, to study the properties or the structure of the material, to determine the makeup of the material based on the reactions. These particles are used to study the scattering of the particle after the impact to create the isotope, and also used for the medical and industrial purposes. Okay, the particle can be accelerated on higher speed in synchrocyclotron. So the principle of synchrocyclotron can be explained with the limitation of the cyclotron, as by the relation of the angular electric field in classical cyclotron. The limiting factor was due to the mass. As the relativistic mass appear, and to compensate this effect, we will compensate the frequency, we will synchronize the frequency. That is the basic principle of the synchrocyclotron. Okay, now let's move further to discuss the construction and working of the synchrocyclotron. The synchrocyclotron consists of one D, and the D is placed inside the poles of an electromagnet. The pole pieces are shaped to provide the magnetic focusing, or the magnetic field must decreased outward from the center for the modification of the relativistic effect. The whole assembly is placed in the chamber, and in this chamber the pressure is kept about 10 raised to the power 6 centimeter of mercury. So higher potential is applied across the D using the power supply. The iron source is placed at the center, and if we discuss about the working principle of synchrocyclotron, it is almost similar to that of the classical cyclotron. The path of the particle is spiral in cyclotron. The iron makes almost 10 raised to the power 5 revolution inside the D's, because there is enough space between the iron source and the target to move in a circular fashion. It will cover a very large distance in the circular motion of the particle. The magnetic field is constant for cyclotron, whereas magnetic field decrease for synchrocyclotron. That is the major difference between the cyclotron and synchrocyclotron. Students were asking me that what is the major difference between the cyclotron and synchrocyclotron. So the major difference is that the cyclotron uses the constant frequency and constant magnetic field, whereas in synchrocyclotron we use variable frequency of the applied field, and if we use the variable magnetic field, we can even circulate the particle in a constant radius. So if we apply the variable magnetic field, we can even circulate the particle in a constant radius. So which is the basic construction and working of the synchrocyclotron. So the difference between the cyclotron and synchrotron is what? That in synchrocyclotron, frequency of the radio frequency oscillator is varied, whereas it was kept constant in cyclotron. And the second difference is that in synchrocyclotron, single D can be used instead of two Ds, the other end of the oscillating voltage supply being connected to the earth. Synchrotron, like cyclotrons, are cyclic accelerators and send particles into a closed loop path, increasing their speed with each revolution. So in synchrotron, particles get accelerated and they get accelerated in each revolution, and their speed will increase in each revolution. But unlike cyclotrons, the synchrotrons loop is not a spiral loop. In fact, since the various tasks a synchrotron must accomplish, like focusing, bending, accelerating the particles into a beam inside a vacuum pipe, that can be accomplished by different assemblies at different times. So the path can be a circle, oval, a polygon with a rounded corners. Okay, so the shape could be of any kind in case of synchrotron, but in case of cyclotron, the shape was only a circular. So in case of synchrotron, the variation could be possible. Okay, let's discuss the principle of acceleration in synchrotron. It's a bit different than that of the cyclotron. We will discuss the development of the synchrotron from the synchrocyclotron, but mainly in synchrotron, the radio frequency waves are used to accelerate the charged particles. How this happens? That a moving charge particle will enter into the field, and an electromagnetic field will resonate with the particle, and particle will get acceleration. How it happens? Let's discuss. The acceleration, the beam is handled by the radio frequency cavity space around the loop. A radio frequency power generator supplies an electromagnetic field to the specially modulated shaped cavity that converts the radio frequency power into the electromagnetic waves that becomes in resonant and built up inside the cavity. When the charged particles enters the cavity, the force and direction of the resulting electromagnetic field will be in the same direction, and the particle will get acceleration. So a moving particle must be entered into the field, and by the resonance principle, electromagnetic waves that we are providing from the radio frequency source will accelerate the particle. So it's one of the drawback of the synchrotron, that synchrotron cannot accelerate particle from the standpoint. The particle should be in a moving position so that an electromagnetic wave can be resonate. You know that the phenomena of resonance can only take place when the wavelength of the moving particle and the wavelength of the wave we are sending will be equal. So both particle and the applied wave should have the same wavelength. Then the resonance will take place and the energy will be transferred that will accelerate the charged particle. So this purpose is achieved by the other accelerator. A linear accelerator will be used to accelerate the charged particle. Then a cyclotron will be used to further accelerate the charged particle. Then it will be injected to the synchrotron, and synchrotron will accelerate the charged particle further to several giga electron volt. So let's discuss the synchrotron in a bit more detail. If we divide the synchrotron in different sections, it will be electron gun, linear accelerator, booster ring, storage ring, beam lines, and experimental station. So the modern synchrotron are based upon the combination of many accelerators. So we can see these modifications here, that the first part is the electron gun, where the ion source will inject the particle, and the electron gun in case of electron cyclotron or ion source in case of proton cyclotron will emit a charged particle into the field. Let's assume that it's an electron, that an electron gun emits the electron using the thermionic emission. You know that by using a step down transformer, if we step up current in a filament, that will give thermionic emission, and that thermionic emission will emit the electrons, thermionic electron, and those thermionic electron will be accelerated using the linear accelerator. So here a linear accelerator was employed to move the particle in linear fashion, and the particle will gain the necessary speed in a linear accelerator, and after that the linear accelerator will transfer the particle into the next system. So the electron gun feeds the electron into the linear accelerator. These electrons are pushed into the linear accelerator by a microwave radio frequency field. The linear accelerator the linear accelerator produces electron pulses that travel in evacuated chamber having a low pressure. Then the electron will be entered to the booster ring. The electron receives a boost in energy when they circulate under the action of the magnetic field in the booster ring. It means the booster ring accelerates electron stream further using the strong magnetic field. Here the radius will kept constant. The strength of the magnetic field increases with the energy of the particle to maintain their orbital radius constant. In addition, the frequency of the accelerating electric field must be maintained or adjusted in order to synchronize with the orbital frequency of the electron. So here we are applying the variation of two things, variation of the magnetic field and variation of the frequency of the oscillating field. So in addition to the frequency of the accelerating electric field must be maintained or adjusted in order to synchronize with the orbital frequency of the electron. So the bunches of electron turns into a fine beam due to the magnetic confinement. Here the bunches of the electron turns into the fine beam when spread electron increases close to the speed of light within these evacuated chamber. Then after a designated necessary speed into the booster ring, which depends on the capacity of the booster ring, means the capacity of this cyclotron. Booster ring is a cyclotron, and by the capacity of this accelerator, the particle will be accelerated to a maximum speed. Then it will be injected to the next ring, that is the storage ring. The injection system transfers the electron from the booster ring to the storage ring. The storage ring is not a true circle, but it can be designed in a polygon manner. The electrons circulate for 4 to 12 hours and produce photons. Why they produce photons? The dipole magnets changes the direction of the flow of the electron, and when the direction will be changed, the electron will be slowed down, and this slowing down of the electron will reduce the energy of the electron, and this difference of energy will be appeared in the form of the photon. So different beam lines are designed here. So the storage ring is really a series of number of sections. After each turn there is a photon port to allow, you can see that the photon port is here. After each section, the photon port to allow the light to travel down to the beam line to the research station where the different experiments would be designed. You can see here, here is a beam line is coming, and after the bending of the electron beam, the photon will release from here, and that photon will applied in an experiment to investigate structural modification, radiotherapy, to study the nuclear reaction, and many more. Okay, so experimental station. In experimental station, each beam line has an optical cabin. An experimental cabin control system. This is the optical control system, means we are using the optical instruments to study the radiation. So the experimental cabin contains the support mechanism, and this certainly we have a specific environment to study the specific sample. So the control cabin allows the researchers to control the experiments and to collect the data in different experiments. Hence, synchronized radiations are put to use the experimental workstations. So in this diagram, you can see that the clear picture of the operation of a synchrotron. Here, a linear accelerator was used to accelerate the charged particle in a linear fashion. Then the particle will move into the next stage and it will accelerate it into the booster ring, and after necessary speed gained in the booster ring, the injector system will transfer the particle to the storage ring, where it can spend several hours. And these dots and these lines are the experimental station. After each magnet, the particle will bend and provide the photon, and these photons will be utilized to study the different experiments. What kind of studies can be performed? There are number of applications of the synchrotrons. I am giving some of them. So the material engineering can be performed. We can study the structure of the material. We can perform the material modification. We can perform the coatings of the material, as like the ceramic coatings can be performed to enhance the durability and to enhance the strength of the material. Magnetic imaging and therapies are performed with the beams of the synchrotron, because the beams of the synchrotrons can be of the variable frequency or can be of the variable wavelength. So these variable wavelength can be adjusted to the ionizing range or to the wavelength of the X-rays that can be used to study the radiotherapy and can be used to study the diagnostic imaging. Okay, synchrotron radiations can also be used for the environmental study, to study the pollution, to study the environmental effects on the material, to study the aging of the material, to study the environmental changing in the form of wear and corrosion on the material. On the other hand, synchrotrons can also be used to study the forensic changes, means forensic changes, as I have mentioned, that aging of the stones, aging of the paintings, or materials modifications can be studied. So the different forensic studies can be documented with the beam of the cyclotron. So synchrotron radiations can be used to evaluate the performance of the microchips. So it's a long subject application of the synchrotron. For example, I would like to mention here that one of the biggest experiment on the earth have been designed by using the synchrotron radiation, that is the Large Hadron Collider. I would like to mention in the coming lectures that what is Large Hadron Collider, and you will get an assignment probably about the Large Hadron Collider, which is the world's biggest experiment where two protons are accelerated up to the tera electron volts, and they collide together, and those collisions will be used to study the early birth of the universe, to study the Big Bang, to study the quark gluon plasma, to study the medical imaging. So there are number of fields are associated with the Large Hadron Collider. It was designed in the CERN, that is situated in the Switzerland. So Pakistan is the member state, and many of the Pakistani scientists have been working on the Large Hadron Collider. That is the collection of one of the biggest cyclotron, biggest synchrotron, biggest accelerators in the world. So it's all about the synchrotron. So in the next lecture, in the coming lecture, we shall discuss about the betatron. Betatron is a particle accelerator that is used to accelerate the electron. Okay, it's all about the particle accelerators, charge particle accelerators, where we studied the linear accelerator, cyclotron and synchrotron, and next we shall study the betatron. Okay, it's all about today. See you in the next lecture. Okay, Allah Hafiz.